So we're going to work through a few problems here to help us practice how we do Hess's Law type problems. So I'm going to have a few tips and strategies first, then we'll have a couple of problems that we'll work through that are sort of the more traditional Hess's Law type problems where you're looking at chemical equations and you're just sort of flipping them, and then we'll return to our discussion of lattice energy. When we talked about lattice energy earlier in the semester, we really sort of kept this quantitative piece out of it, and so we're going to reconcile that and do that big quantitative Hess's Law type problem with our lattice energy sort of situation. So some tips and strategies when you're doing a Hess's Law problem. As our video that you watched, kind of the lecture portion of the video highlighted, when we want to determine delta H for a chemical reaction, we can do it in a couple of ways. We can use experimental methods as a way to determine the heat that's given off from a reaction and use that as a proxy for delta H. Or we can use these empirical or calculation-based methods, which sometimes aren't the reality of what's happening. We're, taking molecules completely apart and putting them back together, but it's a calculation-based method as a way to determine what delta H is. So here's some tips and strategies for how to do delta H or Hess's Law empirical calculations. So you want to begin by looking at each given equation, and you're going to ask the questions here. Is that equation in the right direction? Remember, we're going to be comparing this to a target equation that we're looking at, our final equation. Are the species on the same side as we'd expect them to be in our final equation? If not, that is an equation that you need to flip. You're going to reverse the reaction, meaning that reactants become products and products become reactants. And that also means you need to change the sign on delta H. So if it was exothermic, negative, it becomes positive, endothermic. Next, you need to ask the question, does it have the right coefficients? That is, are the species in the same amounts as your final equation? Be careful with this, particularly if there are things that appear in multiple equations, because they might add up to the overall amount that you want without needing to scale. So keep that in mind first, but if not, you must scale your equation. That is, you're going to multiply or divide by the same number. So all of your coefficients are going to be scaled up or down, and that also means you're going to be scaling your delta H value, okay? Notice that you can flip and scale chemical equations. It's not like this is an either or thing. My recommendation is after you figure out what things need to be flipped or scaled, write down, again, next to those original equations, whether you're flipping or scaling them, what you're doing, and then rewrite each equation, correspondingly manipulating the delta H value as you need. And then make sure that you can sum everything up. It's super easy to make mistakes here. If you think that you're scaling or flipping or doing something, but you forget to do it because you don't have it written down, and it's easy to make a mistake. So our first couple of problems that we'll work through will show you exactly what I mean by that. Again, if you don't arrive at your target equation after you add everything up, make sure you didn't make a mistake. Forget a coefficient, something like that, that would allow you to make sure that your equations sum up to your overall. Okay, so let's walk through a problem here. So first problem here, here's our target equation. Calculate delta H4. So here's how you know when you have a Hess's Law problem. You're going to be asked to calculate delta H for a reaction, and you're going to be given a list of other chemical reactions, right? That's kind of a clue, one of those things that tells you this is that kind of problem that I have. So this is my target equation. So my target equation is here. So I know I need to add everything up to that. I'm going to label these reactions 1 and 2 up here so that we can easily sort of see which one we're talking about when we're manipulating things. So if I'm looking at species that I have, right, I'm looking at, for example, NH3. Well, I can see that NH3 is a reactant here and it's a product here. Okay, so this is a good sign that this is an equation that I'm going to need to flip. Okay, and I also am noting that I have 2 NH3s in this equation and I have 4 in my target. So that's a good indication that I might need some scaling to happen. And because there's only 2 chemical equations here and I don't have NH3 appear in another equation, I feel pretty confident that I can indicate that I'm going to scale that equation right away. Let's take a look at our second equation here. So in this case, I've got H2 on the left. I don't see H2, so let's move on to something else. But I'm noting here that I see H2 in this other equation. So these are going to be things that cancel out. They're not things that appear in our overall target equation. How about O2? O2 is on the left. O2's on the right. Another indication that I need to flip a chemical equation. So I'm going to be flipping this one and noting here that I had one O2 on the left and three O2's on the right. That's a good indication that I'm going to need to flip this equation. So that's that first strategy, comparing your equations, identifying the kinds of manipulations that you need to do, whether they're flipping the equations, scaling them, or in this case, both. Now, my next recommendation is to take this extra time and rewrite those manipulated equations in their correct form. So I'm going to go ahead and scale and flip that first reaction, which means I'm going to have N2 now as 2N2 on the left, and then I'm going to have 6H2, and then I'm going to generate 4 NH3. Okay, so that's our overall equation as we flipped it and scaled it. Now, what we need to do with our, and I'm going to call this delta H1, when we manipulate this equation, when I flip it, I change the sign so that positive, that endothermic reaction becomes exothermic, and then I need to scale up that enthalpy value by twofold as well. So it's minus 184 kilojoules. Okay, so that's what we're going to have there. Do the same thing now for my next equation. I'm going to flip it, scale it by 3, so I'm going to have 6 water now as a reactant, making 6 H2 plus 3 O2. So my delta H2 now, again, is going to become positive because I'm flipping it. So it's going to be a positive. If you don't write the positive, that's okay, but it's always a good reminder that we need to be thinking about the sign of our delta H. And then 1452 kilojoules is what I get when I multiply 484 by 3. So go ahead now and we're going to sum everything up, noting that if things appear on the left and the right side of the chemical equation, we can cancel them. And make sure it's not just as simple as if there was H2 on both sides, I cancel it out. In this case, there's equal amounts, so that's why it totally cancels out. If you had 6H2 on the left and then 3H2 on the right, the net would be 3H2 on the left. But in this case, they completely cancel one another out. Anything that appears on the left side stays on the left side. So I'm going to have 2N2 gas plus 6 H2O gas generates 4 NH3 gas plus 3 O2 gas. And you'll notice that this matches our target equation. Now remember, when we're writing things in the order that we have them, as long as things are reactants and products specifically, the order doesn't matter. So these two, same order as we have over here. The fact that these are written in a different order, that's still the same chemical equation. Okay, so delta H for our target equation then, I just add up those enthalpies. So it's going to be positive 1268 kilojoules is my final answer. Okay, so that one was pretty straightforward. Some of the things that can make a Hess's Law problem a little bit more challenging is maybe you are given sort of distractor equations. You're given a laundry list of equations, but maybe you don't need to use all of them. So that's something to think about as you're working through sort of Hess's Law problems here. All right, so let's work on another problem here. Here's another one. If you want, go ahead and pause the video, see if you can work through the answer. I'm going to tell you that the answer is minus 103.4 kilojoules. Okay, so again, I'm going to work through it here, but if you want to practice and try on your own, go ahead. So if I'm looking at what I have here, okay, so again, this is my target equation. And then here's my equations that I need to manipulate. Going a little bit more quickly here, we can see here that both of these equations are now going to be having things that we need to flip, because my first target equation here has N2. That's not on the right side, so that's an indication. I also can see that it's not in the right amount. So this again is a flip equation, and then I'm going to need to scale it. In this case, I'm going to need to double in order to get up to my target equation. And looking at this next equation here, I can look at NOCl. NOCl is not on the right side, so another indication this is an equation that needs to be flipped. And I'm going to have another scale, so I'm going to need to scale that. So again, strongly encourage you to rewrite these equations. It's super easy to miss a coefficient, forget to manipulate a delta H value. We want to make sure that we get everything correct here. So I'm going to flip this. So it's going to be 2NO gas going to N2 gas plus O2 gas. Delta H, again, I flipped and I scaled this, so I'm going to make this negative and I'm going to multiply it by 2, so 180.6 kilojoules, okay? Same thing with the second equation, flipped and scaled. So it's going to be 2 NOCl goes to 2 NO plus Cl2 gas, okay? Flipping and scaling, I'm changing the sign, multiplying by 2, so it's positive 77.2 kilojoules. Okay, I'm going to sum these up. I can see that there is somebody who cancels here, right? I've got 2NO appearing as a reactant, as a product, so this is going to cancel out, okay? And just to introduce a term that we're going to see, this is going to be called an intermediate. So that NO gas is what we call an intermediate. Okay? It's a reactant, it's a product of one reaction that becomes a reactant for another. So if we were to sort of think about these in a sequential order, this reaction could happen first, we'd make that NO, then it could be used and decomposed in our second reaction to give our product, the other products that we have here. So again, summing up, here's our overall equation. 2 NOCl gas goes to N2 gas plus O2 gas plus Cl2 gas, okay? Delta H, simply adding up all of those enthalpy values, this is minus 103.4 kilojoules. Okay, so just as a little preview for what we're going to see in our next lecture, okay, is this equation is related to something that we call delta HF. Okay, so delta HF is an enthalpy of formation. That's what that little F means here. That means the enthalpy of formation. So this is actually a, see if this makes sense here, this is a negative delta HF equation. Okay, here's why. If you had to write an enthalpy of formation equation, that means you are going to be making, and actually I should say that this is even more than this, this is 1/2 of a reverse enthalpy equation. See if this makes sense. We're going to get to this in our next lecture. An enthalpy of formation equation is an equation that allows us to create 1 mole of a compound from its elements in their elemental form. Okay, so if we were to write a delta HF equation here for NOCl, it would be 1/2 N2 plus 1/2 O2 plus 1/2 Cl2 makes 1 mole of NOCl. That's a delta H of formation. That's a formation equation. We're forming 1 mole of a compound from its atoms that are in their elemental form. Okay, so what we actually have here is the flip of that. So there's that minus, and it's a scale, okay? Because this actually is, I should have put in, that's my fault here. What we've written here is a double of an enthalpy equation. Sorry, it's a double because we're making 2 moles that we have there. Okay, so that's an enthalpy of formation equation. The last thing I want to do here is take a little bit of time and review things that we've talked about with lattice energy. So when we learned about lattice energy, we sort of talked about what lattice energy was, and we used this as a way when we're talking about building molecules and so forth. We had this imaginary process that we imagined sort of separating all the pieces together before, or separating all the pieces before putting them back together. Okay, so we're going to review sort of that construct, but now we're actually going to do the math with it. Okay, so remember when we were talking about lithium fluoride, and we said we wanted to make lithium fluoride from its elements. That meant we wanted to make it from solid lithium and fluorine gas, which is a diatomic gas, so F2 gas. Okay, and we were interested in what was the energy sort of for this overall process, right? How much energy would it take to take lithium metal, combine it with fluorine gas, and make a salt. I tell you, there's a lot of energy, because if you were to take very reactive lithium metal and put it with fluorine gas, it would cause an explosion. It's really quite a violent reaction. That's because we have a large downhill energy. But as a way to figure out exactly how much energy that was worth, we did this empirical thought process. Okay, we're going to do the calculations and the math with it. And we said, let's imagine taking apart all of these pieces and then ultimately having our lattice energy that allows those gaseous ions to come together to make a salt. So I'm going to take a little bit of time here, walk back through this so this makes sense. Okay, and then every one of these arrows has a numerical piece to it. Now that we know how to manipulate delta H values and things like that, we're going to look at how we could use this in a quantitative way. Okay, so if we want to make lithium fluoride salt, starting with lithium metal and F2 gas, okay, here's the things that we need to do. And it's not that they necessarily have to happen exactly in this order, but I want you to know what these steps are. And importantly, I want you to be able to name them and say what they are. Okay, so here's this first thing. Okay, the first thing is we need to take all of those atoms of lithium that are together as a solid metal, and we need to put them into the gas phase. And we call this atomization. So I'm going to write this on here. I'll have another slide that will kind of highlight this. I do want you to know all of these names. If you look at your practice quiz, you'll see that one of the questions is being able to label and name all of these. So this is atomization. Taking solid lithium metal and making it into a gas. So here's what we did. We took solid lithium metal and we make it into a gas. So kind of that's the first piece that we have here. So atomization, taking solid lithium metal and making it into a gas. So if we look at our pictures here, we can see what's happening. We haven't done anything to F2 yet. So we took solid lithium metal and we made them into gaseous atoms of lithium. Okay, next thing that we're going to do is we're going to do a little work with fluorine. So we're going to take fluorine, that's a diatomic gas, and we're going to break that fluorine-fluorine single bond, and now we're going to have fluorine atoms in the gas phase. Okay, so this has to do with bond energy. So if we're sort of thinking about what we want to related to things that we've talked about before, okay, this little piece here has to do with the bond energy of fluorine 2. And so that was table 9.2. Maybe you remember when we talked about, how we could break any kind of different bonds. And so right up here, if we've got fluorine, if we were to write a nice Lewis structure here for fluorine, right, one single bond that we need to break, and we're going to get it to be fluorine atoms there now in the gas phase. So this sort of atomization piece that we have here relating to the bond energy of fluorine, that's going to be basically taking fluorine gas, let me write it from here, fluorine gas, and making fluorine atoms. So now we've got both of these atoms sitting here in the gas phase. Okay, now what we need to do is we need to make them independently into ions. So there's two things that we're going to be talking about here. Okay, first is IE, and so this is ionization energy. So ionization energy. And ionization energy is always the energy to remove an electron. And hopefully it's not a stretch for you to remember that what we need to remove an electron from, I'm going to change colors here just to highlight. So this ionization energy is basically taking lithium as a neutral atom and making a cation by removing an electron. It always is going to take energy to remove electrons. So that's an uphill. We can see this in our picture here. Now we've taken lithium as a neutral atom and we've made lithium cations. Notice the cations are smaller. Remember, when we make cations, they get smaller. The next piece that we're going to have here is we are going to take and make the other ions. We're going to take fluorine as a neutral atom and we're going to take fluoride as an ion. And this is electron affinity, or EA. Notice in this case, and this happens to be because fluorine is the most electronegative atom, really wants to take on an electron, so that's actually a downhill. That's one of our gains. That's going to be a negative delta H value. We're going downhill in energy. But again, we can see what happens here is we're taking fluorine as neutral atoms and we're making fluoride anions. Okay, so here, that's down this picture here. So we've got these fluoride anions. Okay, and now when we have this situation, and this again is not something that happens in reality, we've got gaseous lithium cations and gaseous fluoride anions. Again, notice that these fluoride anions, they got bigger, take on electrons, would become bigger. Now, the attractive force between these is so great that they are going to crash down and become this very ordered ionic solid. Okay? Notice that this is the negative of lattice energy. We define lattice energy as the energy to take a salt and make it into gaseous ions. Again, not something we think about doing. You don't take, table salt and put it in a pan on your stove and you heat it and all of a sudden you've got, sodium cations and fluoride anions that are floating around your kitchen, right? That doesn't happen, okay? But the idea is, with this problem, if we knew all 5 of these orange arrows, right? 3 of them being costs, 2 of them being gains, the net sum of those would give us what the overall energy would be for this process of taking solid lithium metal, combining it with fluorine gas, and generating lithium fluoride. Okay, so that was a long review, right, for that sort of process. But what we're going to do now is we're going to see and calculate what these values are. Or another way to think about this, I can manipulate this problem to have a whole bunch of different kinds of problems. Notice that there's 1, 2, 3, 4, 5, 6 different arrows. If one of those pieces, if one of those arrows is missing, you can solve for it by using the other pieces, right? Because all of these orange arrows add up to the black arrow. So if one of those orange arrows was missing, you could figure it out if you knew what the overall was, okay? So that's sort of the process of how this becomes a quantitative Hess's law type problem, okay? So let's look at this specifically for this lithium fluoride example, right? So here's all of these things that we talked about. This is this atomization. I'm going to write these down here. I want you to know these names. This is atomization, right? That's going to be a cost. That's why it's a positive delta H. This is bond energy. When we need to split those 2 fluorine atoms apart, when they're in diatomic fluorine gas and make them into gaseous fluorine atoms, that's bond energy. This is ionization energy. So ionization energy, right, is the process where we're going to be taking an electron away from that lithium gaseous atom. And then we've got electron affinity. Electron affinity is where we have something take on. It becomes an anion. This is going to be a favorable process, an exothermic reaction for fluorine because it's happy to take on an electron. So it's a negative enthalpy value there. And then the last thing is our lattice energy. And if we wanted to run this problem, let's say, as a calculate what the lattice energy was, okay? Again, this is going to be the negative of what the lattice energy is, because lattice energy is always going to be a positive delta H value because that's the energy that it takes to take a salt and make it into its gaseous ions. So if we're looking at the reverse of this, that's why that delta H is reversed, okay? And then here, this is the delta H of formation equation. If we want to talk about a formation of lithium fluoride, we're going to make it from its elements in their elemental form. So it's lithium solid, and then 1/2 of a mole of fluorine gas is going to get us to lithium fluoride. So look at this, that's the delta HF value. So let's imagine that we knew that value. We can use this then to calculate our lattice energy. So keep in mind, with these problems, any one of these enthalpy values could be an unknown, okay? They need to sum up to your overall, but you can use some basic algebra then to figure out sort of what your unknown is here. And this tells us then X would be minus 1050 joules, okay, to put these guys together. So that tells us that it's a positive value for our lattice energy of 1050 joules. And again, that's the energy gained by forming an ionic solid from its gaseous ions. Again, that was that missing gain that we had here. When we were first looking at this problem, we were saying sort of what was this? So lots of different ways you can manipulate these. I'm going to do one more piece here and have us think about this, okay? So this is sort of a giant Hess's law problem, okay, looking at sort of this lattice energy. So this is looking at the same kind of piece. I want to use the following to calculate the lattice energy of magnesium fluoride. So not lithium fluoride, let's look at magnesium fluoride, okay? So if we want to talk about the lattice energy of magnesium fluoride, we need to think about, well, how would I write that? What is that target equation? So that target equation, okay, lattice energy for magnesium fluoride means my target equation is magnesium fluoride as a solid being made into magnesium cations as a gas. I know it feels really weird to write like a magnesium cation as a gas, but that's what this is. And then 2 fluoride anions as a gas. Okay, so that is going to be what our target equation is. So remember, we need to look at the equations that are given and ask, are they given like we'd expect? Okay, so for example, here's this first one, magnesium solid, magnesium gas. Okay, well in this case, I don't necessarily see those in what I have here. So this is my atomization equation. So I want you to be able to label these. And then again, we're going to see sort of where things need to appear or disappear and so forth. This is going to be our bond energy equation. So I'm just going to abbreviate that, bond energy. Okay. I'm looking for things, as I'm looking for these equations, I'm looking for pieces that I know appear in my target equation. I haven't seen things yet that are in these equations that appear in my target one. Magnesium gas plus magnesium cation plus an electron. This is actually ionization energy 1. This is the energy that it takes to remove that first electron. Now, because I have a divalent cation, I'm going to have 2 ionization energies. Okay, so 2 ionization energies there. And now I'm starting to see things that appear in my target equation. Okay, so I've got fluorine gas plus an electron makes fluoride ions in the gas. So this is my electron affinity. Okay, so I want you to be able to label these and so forth. Okay, and then this last one, I've got magnesium solid plus fluorine gas makes magnesium fluoride as a solid. This is delta HF. That's a delta HF equation. So qualitative and quantitative pieces here, just to highlight for you. I would expect you to be able to write any one of these kind of types of equations. I wouldn't expect you to know the numbers or the values that we have here, but I'd expect you to be able to sort of write what these pieces are. Write a first ionization energy equation for magnesium. You should be able to write that, okay? Now, as I'm looking at things here, hopefully you can recognize and see that I am probably going to need to scale, okay, this equation. So this equation right here is going to need to be scaled. And how do I know that? Well, I'm looking at the fact that I need to have 2 fluorides in my equation, and I only have 1 there. That's going to be a problem. Okay, something else is I'm looking at my target equations and things that I have here. My target equation has magnesium fluoride as a solid. Okay, I've got magnesium fluoride as a solid here, but it's a product. Okay, so this is an indication that this is an equation I'm probably going to need to flip. And for right now, I'm not going to touch anything else because there's a good chance that a lot of this is going to sort of reconcile itself once I handle the scaling and the flipping of these 2 equations. So just to make sure to highlight, if I'm scaling this equation, that means I'm going to leave the sign, but I'm going to need to multiply that by 2. And then if I'm flipping my last equation, all that means is I'm going to change the sign there. Okay, so I'm going to flip my page here. I'm going to have handwritten, but these same equations, but now I'm going to have done this manipulation. I'm going to have scaled this equation and flipped this equation and fixed their corresponding delta H values, okay? So if you want, go ahead, pause the video, try writing those kind of in their flipped forms, their scaled forms for yourself, see if you get the same pieces, and then what we're going to do is go through and see if we can cancel everything out to get our target equation. Okay, so gone ahead and done that. So here, these four equations, we didn't do anything to. Again, here's what they are. We've kind of labeled them. I've scaled and flipped these last two equations. So the last piece here is to say, do these sum up to our overall target equation? Okay, so what we're going to do is we're going to go through and we're going to find things that we could cancel out. Okay, well, let's see here. I've got magnesium. I'm just going to start at the top here. Magnesium solid is going to cancel out. Magnesium gas is going to cancel out. So that first equation is taken care of. I've reconciled everything. Something that was a product of one reaction is now a reactant for another. Okay, I've got F2 gas. Okay, that's going to cancel down here. I've got 2 fluorine atoms here. 2 fluorine atoms, yep, those are going to cancel there. Okay, I've got a magnesium plus cation. Well, I'm not going to have a magnesium plus cation. Okay, now if I'm looking at what's left, I've got a magnesium 2 plus, but you know what? I want that to stay. That's going to be in my target equation. I've got 2 fluorides that I want to stay. They're in my target equation. Okay, and then I've got MgF2 solid. That's in my target equation. Last thing I just want to look at and remedy is, yep, I've got 2 electrons on my right, 2 electrons there on my left, so those are going to cancel out. So if I'm highlighting the pieces that are sort of left over, okay, I've got this piece, I've got this piece, and then I've got that piece. So I'm going to keep them in the same place that they are. I've got MgF2 solid, okay, goes to Mg2 plus gas plus 2F minus gas, okay? So now we need to go ahead and add up all of these enthalpy values. And the delta H for this is going to be a large positive number, is 2,962 kilojoules. It's a positive value. This is the lattice energy. So this is delta H of lattice for MgF2. And if we think about this, maybe we didn't see it on this last slide here. It asked us to, once we calculate that, compare it to the lattice energy of lithium fluoride, which is 1050, for sodium chloride, which is 788, and see if it makes sense that it's larger. Well, it should. Remember, when we learned about lattice energy, and you just had to rank lattice energies, right? The stronger the attraction for those ions, the higher the lattice energy. So when we have something that's a +2 charge with fluorine as fluoride, that's going to be a larger lattice energy. And so we'd expect this to be larger. So I know that was a lot, but keep in mind that all this really is a big Hess's law problem. But there's several things that I need to make sure that you know about this problem. Kind of reviewing things. I want you to know what these names are and be able to write an equation that would correspond to this, either for a real atom, or if I were to give you just a generic metal or something like that, that you could write an atomization equation, what bond energy looks like, ionization energy, electron affinity, a delta H of formation equation, or a lattice energy equation. So be able to think about this sort of qualitatively in that regard, and then also be able to do a more involved quantitative Hess's law problem.